Welcome, and thank you for joining us for today's webinar, Real-Time Fiber Optic Strain and Shape Sensing Technology, sponsored by Luna Innovations, a manufacturer of cost-effective fiber optic distributed strain systems that produce real-time strain measurements with very small gauge lengths using any off-the-shelf fiber or Bragg grading fiber. Oz Optics Limited, a company that designs and manufactures fiber optic components, test equipment, and sensors, including an award-winning sensor that is able to measure simultaneously strain and temperature along a telecom fiber. And TechBriefs Media. I'm Bruce Bennett, editor at TechBriefs Media, and I'll be your moderator today. This webinar, which will last approximately 60 minutes, will focus on a patented lightweight fiber optics interrogation algorithm that can be used for real-time wing shape sensing, temperature, and strain measurements. There will be a question and answer period at the end of the presentation. If you have a question, you may submit it at any time during the presentation by entering it in the box at the bottom of your screen. Our presenters will answer as many questions as possible at the conclusion of the presentation, and participants will receive a follow-up email with instructions for downloading the presentation and viewing the archived version of the webinar. In order to view the presentation properly, please disable any pop-up blockers you may have on your browser. At this time, I'd like to introduce today's speakers, Ronald Young, Lance Richards, and Alan Parker. Our main speaker, Ronald Young, is Chief of the Innovative Partnerships Office at NASA's Dryden Flight Research Center at Edwards, California. As such, he is responsible for working with center technologists and external partners in managing activities to transfer technologies developed at NASA Dryden to the private and public sectors in the United States for commercialization. Mr. Young, who holds Bachelor of Science and Master of Science degrees in electrical engineering from the University of California at Davis, received the NASA Exceptional Service Medal in 1997 and the NASA Small Business Technical Person of 2008 Award. He will be joined today by Lance Richards, the Structures Research Engineer, and Alan Parker, a Systems Research Engineer at NASA Dryden Flight Research Center. At this time, I will hand the program over to you, gentlemen.
Thank you, Bruce. This is Ron, and I appreciate this opportunity that you and NASA TechBrief Media Group has put on these series of webinars for NASA to provide opportunity for us to showcase some of the work and innovation that has come out of NASA and our center here at Edwards, California. I'm Ron Young, the head of the IPO office, and today we'd like to give you a little bit of an overview of who and what Dryden is and what we do here, and some of the innovations that are available for licensing from our work. Dryden Flight Research Center is located in Southern California in the Mojave High Desert on Edwards Air Force Base. NASA and its predecessor organization, NACA, has a presence here dating back to the 1940s when Chuck Yeager first broke the sound barrier. And today, Dryden is continuing its work here at Edwards as the NASA High-Speed Atmospheric Flight Operations Center. And I would like to talk a little bit about today's mission that we have for advancing technology and science through flight activities here. Our facility has a number of diverse aircraft for experimental tests, as well as unmanned vehicles, airborne platforms, and the range systems and test facilities to conduct those activities. Our center has a competency in flight safety and risk management. We offer project and mission management support for testing of novel and experimental aircraft for both piloted and unmanned systems. The Dryden office, Innovative Office, works with many of our programs here at Dryden in the technology development areas, and we manage the technologies for commercialization and utilization beyond NASA applications. We do this to try to broadly disseminate technology for the benefit of the U.S. public. We offer collaborative opportunities with private entities and other government agencies to develop technology transfer, licensing, and partnership opportunities. Additionally, our office supports small business innovative programs, both SBIR and STTRs, for using these developed technologies for mission use as well as commercialization. I would like to talk a bit about some of the work here. Traditionally, our work at Dryden is in the aeronautics area. We have a long history of high-speed work, including Supersonics, and current day efforts are involved with sonic boom investigations, where we are working to enable high-speed overland cruise capabilities to minimize, by minimizing the sonic boom impact on populated areas. Currently, some of the work that has resulted from that has resulted in capabilities that are available for licensing for sonic boom footprint predictions. This technology is being used in our flight research and experimentation to guide piloted aircraft flying supersonically in order to be able to place sonic boom impact over land in desired location, thereby minimizing impact to populated area. Next chart, please. In the area of collision avoidance, we have worked with both the U.S. Air Force as well as other parties to develop technologies to take advantage of automatic collision avoidance technologies for piloted aircraft, using ground terrain mapping data to avoid collisions impacts with the ground. We have real-time decompression capabilities that have potentials for other applications. These patent-pending technologies can be tailored to suit user requirements for decompression of data that are suitable for compact devices such as tablets and smartphones. And as Bruce talked about today, I would like to talk about the work in the fiber optics area. The Icona aircraft is a platform that has been used to develop some of these technologies for applications for large flexible structures that have flown on the Icona. Icona is a civilian version of a military Predator B aircraft that is used for remote sensing application and long endurance flight. And the fiber optic system has been used on this to determine wing shape, to try to improve aero efficiencies for these types of missions. With that overview, I'd like to try to hand this over to Lance Richards at this point, who will actually dwell into today's topic of fiber optic sensors.
Okay, thank you, Ron. First of all, welcome everybody. Thank you for joining us. We're really excited about the prospect of going through the presentation and giving you an overview of the work that we've done at NASA Dryden over the last 15 or 20 years in the area of fiber optic sensing technology, which we will call many times over the course of the webinar FOSS technology, or fiber optic sensing system technology. Along with me today, we'll be tag teaming this, is Alan Parker. We'll be kind of moving the mic back and forth throughout the presentation. In addition to Alan and myself, Anthony Piazza and Patrick Chan have also been kind of core members of our team. And we're going to go a little bit through this, and you'll see a little bit more about them and their backgrounds as we go through this. But you also notice as we go through these slides that, that there's a lot of collaborators and partners and benefactors over the years. We haven't done this work in a vacuum, and so we want to acknowledge really all the support we receive from other NASA centers and funding sources across the agency. Also, our university partners have been very strategic in helping us advance the technology. So with that, we'll go to the next slide. And, okay, let's see, go back to the topics. What we're going to cover today is a little bit about us and who we are, and then some of the inspiration and the background to the technology so that you understand kind of how it works. And specifically, a lot of the presentation will be focused on the sensing system itself, which is what I think it will be driving a lot of the discussion on. That's been the enabling factor in the licensing and the commercialization part of our work. And then we'll be explaining a lot of how this works through application near the end of the presentation. In fact, most of the presentation will be the application of the technology. So first of all, who we are. We have this team, as I mentioned. Patrick Chan, his background, you see the background of all of us, and our contributions. And Patrick's background is in optics and laser development and research. Alan's background as electrical engineer is in systems design, development. He's also been really key in the processing and visualization, as well as the system development activity for the FOSS system. Anthony, we call Nino, that's his nickname. Piazza is an instrumentation specialist who's been responsible for understanding the measurement, how to characterize it for all the various sundry errors that creep into measurements, how to apply it to a structure, install it, and get accurate results and interpretation. My background as a structures engineer has been mostly with aircraft structures and strain measurement technology. All right, so the background, just to give a little bit of the history, we started this about almost 20 years ago now. We saw the technology and the promise that it and all the benefits that it afforded, and we initiated a development activity really with some seed funding that came about as us, interacting with our colleagues in industry and seeing the technology and saying, well, this is a very promising application for NASA. And so we started first by looking, we're Dryden Flight Research Center, so we started seeing how we could develop the technology so it would be more suitable for our flight applications. But what we noticed was a lot of the activity was being focused on applying it immediately into the environment from which these vehicles would operate. And so we felt like a key to us being able to really understand what was going on and apply it correctly, we needed to develop really a roadmap starting from the lab and understanding the science behind the measurement and evaluating its accuracy by comparing it to strain gauge technology, which is really the gold standard in our community for structural tests and evaluation. So we started working in the labs and increasing. As you see the upper right-hand schematic or picture, we see that we kind of go sort of clockwise around this in increasing complexity, geometric complexity, structural complexity, as well as the applied loads and features that make this that are necessary to get to the aircraft vehicle, the vehicle or space launch vehicle, whatever the application is. We began by a close collaboration with NASA Langley, initially with the patented optical frequency domain reflectometry demodulation technique, which is what OFDR stands for, which is developed at NASA Langley. And then we went off in sort of separate directions and towards our charter as a flight research center to get this into an environment that would provide real-time structural monitoring. At the time, the system was limited based on the infancy of the laser technology. That was limiting its usefulness. And also the systems itself, the processing was not suitable to an aircraft environment where we needed dozens of hertz of response in terms of samples per second. Whereas instead of a benchtop test or benchtop system, which was able only to provide about one sample every 90 seconds, we needed something on the order of 30 to 80 to 100 hertz. So we initiated this program, and the goals were to increase the sample rate and the robustness of the system in order to integrate it onto a vehicle like you see here on the lower right-hand corner of the chart of the slide, which is the F-18 at Dryden. But as a result, after the 15 or 20 years or so, we've developed this comprehensive portfolio of intellectual products that is now ready for commercialization and spin-off, which is what NASA's been doing since the early days. Okay, so now we're going to move into the inspiration and some of the benefits of the technology. Why fiber optic sensing research? When really, to answer the question, it's kind of a no-brainer. You look at a conventional sensor, a conventional strain gauge on the upper right-hand picture. You can just see the contrast between the size and the complexity of that measurement, which provides only a spot or a very localized measurement of strain, compared to what you can see next to it, which is a fiber optic strain sensor. In fact, it should be plural. It is plural, strain sensors, because not only are we measuring one sensor, corresponding to that strain gauge, one measurement, but we're able to discern strain now down to about a 1/16 of an inch. So along that one fiber, every 1/16 of an inch, you have a unique strain measurement, which is comparable to the single strain gauge that you see in that upper right-hand picture. You also can see a fiber optic temperature sensor, which we can decouple that structural strain from that measurement so that it only senses temperature. But basically the benefit here is lightweight, and everything in our industry and aerospace is driven by weight. So if we can cut down the mass fraction of our instrumentation systems and instrumentation sensors, we can increase the payload, we can increase the range, decrease the fuel costs. All those things really are driven by weight, which fiber optics is just that, like I said, a no-brainer. We can multiplex multiple sensors along a single fiber, which I just described, which reduces the bundle sizes and reduces the time to install the fiber. It provides full field strain mapping, which looks mostly now, it can look like a finite element model result in terms of a strain fringe plot. It's small in size, about the size of human hair, which allows it's now amenable to be embedded inside composite materials for damage detection and internal health assessment. It's compatible with the telecommunications industry. It has an inherent safety benefit of not having any sparking or ground looping issues. It's chemically inert and not susceptible to electromagnetic interference or pulsing. So really, like I said, it speaks for itself. It didn't require a lot of vision to be able to see the benefit for the technology. In terms of installing it on structures, it does have numerous advantages as well. Instead of a 4-hour per strain gauge time for curing and adhering to the sensor to the structure, we're able to reduce that by a couple days of installing a 40-foot fiber, which that fiber would have about 2,000 strain sensors on it. So we're able to lay these down very quickly. We've sort of segued our experience with strain gauge technology with adhesives and surface preps and things like that to being able to develop techniques that are comparable with fiber optics. So not too much different there. Minimal time working on the vehicle, so we reduced the time and the schedule, which is, again, that's another driver. Obviously, time is money, and so if we can reduce the time on the vehicle, that's always very, a benefit. But there are, before I move on to the challenges, one of the things for a flight researcher is we want to be able to get sensors on the outside of the vehicle called the outer mold line. That is just kind of a non-starter when you're talking about strain gauge technology, because the disturbance of the flow due to the tripping of the flow over these lead wires. But with fiber optics, the profile is so small that we're able to have really little to no impact on the overall lift or overall aerodynamic performance of these fibers. And we'll show you some of that on subsequent view graphs. But the installation does have some challenges with it. The fibers, to be fair, are a little more fragile than the conventional strain gauges. They're hard to see, so they can easily get caught on a cuff or something as you're just handling the fiber. But once you put it down on the structure, we really haven't seen too many failures. But the handling of it's more of a challenge. There's a minimum bend radius so that you can't have it kinked at all. It is glass, so glass doesn't like to be scored or kinked. And it's not really practical if you're talking about, hey, look, I only want one strain gauge measurement or strain measurement on a certain area of a plate or somewhere. This is not the technology for that. A strain gauge is probably a better choice. So those are some of the installation advantages. One of the key areas of inspiration for us has always been in the human body. So, as you're looking at this model of, a square inch of human skin, it's incredible what kinds of information can be is available and how many sensors can be packed into this little square inch of human skin. You can see kind of the numbers there: 9,000 nerve endings, 600 pain sensors, 75 pressure sensors, etc. God's been doing a great job with this over the years. We're just trying to catch up, and the technology, this continuous grading fiber, is doing a phenomenal job of getting us higher fidelity resolution in composites or on the surface. In this case, I'm showing a schematic of about 16 sensors per inch. And that allows us to get about 200 strain sensors per square inch as a sort of an apples-to-apples comparison, which we have demonstrated in the lab. So that this whole area of smart structures is now, we've been talking about it for a couple decades now, and I think we're getting to that point where we're getting close. But with that, I'll hand over the handset to my colleague, Alan Parker, who will be talking about some of the technology and explaining that in more detail.
Thank you, Lance. As been pointed out, Lance was very thorough and pointed out some of the advantages, so I won't rehash that. But some of the things I do want to just reiterate is just keep in mind that on this hair-like structure, you can have thousands of these strain sensors on this small fiber that you route on your surface. And one of the things that makes this technology slightly different than technology that's currently available that uses fiber bride gratings is that this technology is all of the gratings are written at the same wavelength, which makes it unique, which also makes way for you to have these thousands of gratings on a single fiber. You're not really limited to tens of gratings on a single fiber. Like in conventional strain gauges where you have an excitation source, this technology is no different. You have to have an excitation source to excite these gratings. The excitation source in the OFDR realm is a narrowly bandwidth tunable laser or swept laser. And this swept laser is designed to sweep over a given range of frequencies, which actually represents your strain range over which you're measuring. So as this laser light is being swept over a given set of frequencies, this light is injected into this hair-like structure, this fiber, and it propagates down the fiber. Each one of these gratings, as the laser tunes to its natural frequency of a grating, that grating starts to reflect a small portion of that light. That light is then modulated at a unique frequency, which is unique to its position on the fiber, which allows you to identify one grating from its neighbor. Each grating would have its own unique carrier frequency. I liken it to an FM stereo or FM spectrum where you have the audio band on 102.1 is modulated at a unique frequency to where you can discriminate between one radio station and the other. The same is so in this technology, but it's just that each grating is its own FM radio station, if you want to think of it like that. All of these signals are then reflected, modulated, and summed back at the system. So the system actually is measuring one single signal. And so the task of, next slide, the task of interrogating that signal is kind of the creme of the creme of the technology. How can we effectively and efficiently and quickly interrogate this signal so that we can resolve actual strain or whatever the parameter is we're measuring? What I'm showing here in this slide is just a diagram that overly generalizes the way that we handle these signals. The interrogation process is to simply separate these multiple different frequencies, these multiple different carrier frequencies, and then process each one independently. And one of the most efficient ways of doing this to date is time frequency analysis, such as FFTs and inverse FFTs. Over the years, next slide, over the years, we have developed multiple FOSS or fiber optic sensing system interrogators, each one improving upon its predecessor. What's shown here is, looking at the middle picture there, what's shown here is NASA's current state-of-the-art technology representing all of the innovative algorithms that we've developed here at Dryden over these last few years. Algorithms that allow us to operate this technology in real-time environments at rates up to 100 samples per second. Some of the specifications that we have designed to, and this has been driven by one of the flight programs that we've engaged in, and we'll talk about that in a little bit, but we've tailored our systems to interrogate 8 fibers simultaneously, with each fiber having a max sensing length of 40 feet. And that 40 feet, in that 40 feet of fiber, you can have a sensor every quarter of an inch. And if you do the math, that works out to be about 2,000 sensors per fiber. That's 16,000 sensors per system, scanned at a rate of up to 100 samples per second. Another thing that in addition to the increased performance, the ability to shrink down that technology to what used to be equipment that occupied a optics table, we were able to shrink that down using custom hardware, custom developed modules, custom optics. We've been able to shrink all of that hardware down into a platform of about the size of a shoebox. And since we've been able to do that, we've been able to make possible that which we originally started out doing, and that was to take this technology into a flight environment. So what you see at the top chart, at the top of that chart, is a picture of a flight box, which was ultimately flown on two different platforms. Next slide. So now we're going to move on to the applications. You see a flower here, and I call it a flower. My colleague doesn't like for me to use that term, the term flower, but I like it, so I'm going to stick with it. So we have this flower, and to help us along, we decided to divide the rest of this discussion into specific parameter measurements and the field of use where it's been applied. As we proceed, we will transition clockwise around this flower, starting with strain. So keep in mind that all of this is made possible because of the core FOSS technology, which is at the center of that flower. Next slide. Strain. Strain really is the basic measurement for all of the subsequent parameters that we measure or demonstrate from here on out. We were actually invited by NESC, which is NASA's Engineering Safety Center, to participate in a test that they were conducting at NASA Langley. And this was a collaborative effort between just a host of different NASA centers that actually was responsible for this. But one of the things that they wanted to do in this composite crew module was the design engineers wanted to validate their models, in particular in the critical regions around the hatch and the windows. They wanted to compare empirical strain data captured continuously around these openings in order to accomplish this goal. So what we were invited to do was to come out and instrument that vehicle. We installed 4 fibers around the different openings, which total to about 3,300 strain sensors and measurements of spatial measurements up to a half an inch, sensor every half an inch. And we were able to give the designers a real-time structural indication comparison using 3D graphs for both the air and water pressurization test that was performed up to 200% design limit load. Trying to do this with conventional strain gauges to accomplish this task would just be impractical. So strain values observed from fiber optic sensing, from the fiber optic sensors here, correlated very well with the finite element models, the predictions that they derived under different conditions, to within 5% difference between the predicted and the measured. There was a quote at the end of the program when they were finishing up the documentation. A couple of quotes that they made inside that document was, fiber optics real-time monitoring of test results against analytical predictions were essential in the success of the full-scale test program. And another quote was, in areas of high strain gradients, these techniques were invaluable. I'm going to pass it over to Lance.
Thanks, Alan. And this is the fiber optic schematic that Alan called a flower. I like to call it as a fiber optic bundle, but I guess we can compromise in calling it a fiber optic flower. But anyway, just to kind of reorient where we're headed, we've moved from strain, and now I'll be talking about how we can derive applied loads from these same strain measurements. All right, so you have a slide up now that shows strain and applied loads. And the idea here is with one single fiber installation that measures strain, we can, without any extra physical interaction. We can derive the applied loads just by using really efficient algorithms to input those strain measurements into to get a real-time assessment of applied loads. So this is just the introductory to that. We started with flat plates on simple materials, monolithic materials like aluminum. You can see a figure in the middle, a picture of that of an aluminum plate with some loads on it, and that was instrumented with fiber optics. And you're just seeing some results between what we were able to measure through externally derived loads and our predictions from the strain-based approach. So the bottom line is we're showing good results from our techniques and compared to actually analytical or physical response. So we have good correlation there. But really the challenge is, okay, that's on an aluminum plate, about 36 inches long, really big deal. We want to, we need to be able to see this is going to happen and behave realistically in a good way in flight. Another step towards that is some work that we did with Mississippi State University in partnership with them in their lab on all composite glider wings of about 20-foot wingspan, each half span, so 40 feet in total length. And with the same installation, we can get the strain from root to tip on each wing and the externally applied load. So just as a concept, what we're doing is we're taking in-plane strain measurements in real time, inputting those into ultra-efficient analytical algorithms that calculate out-of-plane applied loads. So that's, and what we show there, I'll show you the results in just a minute, but we are also going to now move into, with that same test setup, the ability to not only measure strain and applied loads, but now move into 2D and 3D shape. All right, so the next chart shows our two different approaches for deflection methods, real-time deflection methods. One is the 2D shape sensing method that we derived at Dryden that takes the structural strains to calculate shape at each one of those very highly resolved strain measurement maps and to calculate shape. The reason we call it 2D shape is that you can use multiple fibers running from root to tip, that if you know the deflected shape ahead of time, like on a wing or on a beam, then this method allows you to get a two-dimensional mapping in the deformation of that as it's subjected to its load. So that is a technique for beams or beam-like structures that are cantilevered or simply supported or what have you. The 3D shape sensing method is one that Dryden's worked with Langley in the past, and we have a technique you might think of now that's applicable to not just beams and plates, but it could be on ropes or cables or fuel lines or anything like that. It has a wide variety of applications, and it takes these strains, and it doesn't depend on structural response now. It immediately calculates a deflected shape based on these three fibers that are located 120 degrees apart, as you can see there. All right, so how do we apply that? Well, now we can go back to the test setup that I mentioned earlier with Mississippi State when they're conducting tests on glider wings that are composites. We can now, in one single test setup and one single installation of a fiber optic from root to tip, we can measure strain, calculate the applied loads out of plane, and also the two-dimensional shape out of plane, all in real time up to those sample rates that Alan described earlier. In flight up to 100 samples per second, or in the ground we can approach that or get about 60 samples per second. So extending that work, those were 40-foot in total wingtip to wingtip span. Now what I'm showing here on the next view graph is the same kind of idea of using strain in two-dimensional shape, but now with our partner at AeroVironment, they have a global observer vehicle that they brought to Dryden, and we did some structural testing of that wing in our lab. And in this case, the goals were to validate their strain predictions along the wingspan. But we're able to install the fiber optics on this in a very efficient way, and then be able to measure these strains from the fiber and also calculate the wing shape. So in this test, with a single system, we were able to measure 17,200 gratings, all in real time from these fibers. So how did it work? Well, here's how it worked. I don't know if the animation is actually built into this test to this presentation, but this shows the overall graphic of the test. So you can see the wing in the upper photo from wingtip to wingtip. That's 175 feet. It's all composite. And you can see the load structure that is consisting of what we call wiffle trees that distribute the loads out to simulate an aerodynamic set of loads. And we loaded this from 100% all the way up to 100% of design limit load. The bottom picture shows same, like a segment of the wing with these photogrammetry targets, which was used as our truth or validating standard to evaluate the wing shape calculations, which I'm going to show on the next slide. All right, so the results from that test, you can see the cross-section of the wing with the 4 fibers that were installed. And I'm showing results from fiber number 3 from root to tip of loads that are applied from 100% of the DLL or design limit load all the way up to 100%. And there's really 2 things that are being compared in essence. The first is our strain-based deflection algorithm along with its corresponding photogrammetry result, which is with the targets in the optical system that we have. And you can see very good correlation between our algorithms and the validating standard. So very pleased with that response. Now I'll turn it over to Alan, who will be talking about that same vehicle as it was transitioned into flight.
Having first demonstrated this technology in the lab on the simple beams, and then taking it to a large-scale testing that we just finished talking about in terms of the wing load test that we've performed in our laboratory, the next obvious step was to actually take this technology and put it in flight, which was our original goal to begin with when we first visited Langley some 15-plus years ago. To date, we have successfully participated in 2 flight programs, and 3 more near-term flight programs to come, probably within the next year or so. We have designed and built an 8-channel system that flew on SOCOM's or Lance mentioned AeroVironment's Global Observer vehicle. We instrumented the left wing of that vehicle with 8 fibers, and somewhat of the same configuration that we did on the wing loads test that was performed on the ground. We also instrumented the fuselage with a single 40-foot long fiber, which gave us a total of 9 fibers on that particular installation. And that fuselage fiber was there to monitor any type of tail movement that was occurring during flight. By the way, Global Observer had its first flight back in August of 2010, and the system was on board for that first flight and all the subsequent flights after that, and it performed very, very well. The second flight application that we were able to participate in was actually prior to the Global Observer. We flew on our Predator B, which is a NASA Dryden aircraft, which we call Icona. On that vehicle, we had 18 successful flights logging about 36 flight hours. The flight program was conducted in 2008, and we still, to date, I believe, have validated the only in-flight validation for fiber Bragg gratings used as strain as well as shape measurement for aircraft. As seen in the previous slides, we showed you the installation, and on the installation slide, we installed 6 fibers, 3 on the left wing and 3 on the right. And they were installed, 1 on the leading edge, 1 on the outside tip, and 1 on the trailing edge of both left and right wing. We had a total of about 3,000 strain measurements that we were measuring on this particular system. And we actually have a video of some data that was actually captured in flight, so we will actually show that now. And what the video will actually show is there's 2 portions to the video. There's an upper chart and then a lower chart. The lower chart is actually a time history chart that shows the left and right wingtip as a maneuver is being performed. We call it an all blue, all brown, all blue, where the pilot would pull back on the stick and then push forward on the stick. The upper chart shows data in the yellow, which represents the strain distribution along the left and right wing, and data in the red that shows the actual wing shape. So let's play that video now. So the video is showing the actual movements, the response from the pilot activating the stick, and you see the time history showing the deflections at the wingtips of the left and right wing. This was a very, very successful flight program for us. We actually had some co-located strain gauges, conventional strain gauges, 8 on each wing to validate our optical strain measurements, and they responded and correlated quite well. Another real-time parameter we have demonstrated successfully is 3D shape measuring, where the 2D shape algorithm uses a single fiber bonded to the surface, yielding an autoplane deflection. The 3D shape algorithm uses a minimum of 3 fibers separated by 120 degrees to render a shape in the XYZ directions. We performed some simulated aluminum plate testing in the lab to validate the concept, and then we were invited by Gulfstream to go and instrument their quiet spike boom for ground test in Savannah, Georgia. So we packed up our bags and we went to Savannah, and we instrumented this 35-foot long quiet spike boom with 5 fibers, making measurements every half inch along these fibers. And so we had a total of about 2,500 strain measurements that we were making. And with that, the boom underwent some loading in the lateral and vertical direction. And you can see in the diagram there how the fibers were actually attached to the surface of the boom while it was extended, not retracted. Next slide. The shape. Here's the data of the 3D shape experiment that we did on the quiet spike. As you can see, with the solid lines, that was data that was collected from their laser measuring device that Gulfstream had on site, and we compared our 3D shape capability of the FOSS system, which is the dotted lines, to that data, and you can see how well they compared here. And by the way, the data is normalized on the y-axis. Next slide. So we've talked about strain, we've talked about applied loads, we've talked about 2 and 3D shape, but another parameter that we are able to measure using this type of technology is temperature as well as cryogenic liquid level. A year and a half ago, we were asked by Kennedy Space Center and Launch Services if our fibers could be used to measure cryogenic liquid level on fuel tanks for launch vehicles. So we were asked to go and participate at a test at Marshall Space Flight Center, where KSC was sponsoring some cryogenic testing. And we did that so that we can get a feel of what was involved in making this measurement. As we went out and actually instrumented a text fixture with our fiber, we ascertained that by using the FOSS temperature measurement capability alone was not sufficient to detect the actual transition region between the gas and the liquid because of the temperature gradients are so small. We just didn't have that type of capability within the FOSS technology to resolve down to those levels. So we came back to the lab at Dryden and developed a unique fiber structure and a real-time interrogation process algorithm that would allow us to accurately detect the location of this boundary layer to within 1/4 of an inch. And in some cases, we were able to get as low as 1/16 of an inch. Next slide. So we returned to Marshall Space Flight Center with this newly developed sensor. to conduct some experiments in their liquid hydrogen test facility. We wanted to try to see if we can actually measure liquid level in a liquid hydrogen dewar where we had liquid hydrogen in the liquid state as well as in the gas state, and try to measure where that boundary layer was. And to be able to validate that measurement, we simply used a borescope that was located inside the contained dewar, as well as a ruler, a simple ruler, to look at where the measurement is. We also had within that same environment a cryo tracker, which is a commercially available device that does liquid level measurements using silicon diodes, as well as a Marshall developed silicon diode rate. And so we had these three different instruments located inside this dewar, and we performed multiple fill and drain procedures where we filled it to 20%, I think it was 40%, and then around 60% fill levels. And in doing so, we compared all four different techniques, the borescope ruler versus the CryoFOSS, which is the sensor that I've been referring to, along with the cryo tracker and the Marshall silicon diode rake. And the results are on the next slide. The one in particular that I want you to look at are on the left bar chart is the red and purple. The purple actually represents the borescope and the ruler. That's what we consider the standard. The red represents the CryoFOSS, the newly developed device that we were out there to validate. So we were actually able to track to within a quarter of an inch alongside the borescope. So we felt that that was a very, very successful test. Here's Lance.
Okay, thank you. Now we're moving from the cryogenic and temperature sensing technologies to the embedded strain measurement technologies that we kind of alluded to earlier by marching around this flower. Slide 37, we're showing a slide here of embedded strain. And really what we saw early on in the program was some challenges with embedding fiber Bragg gratings in composites. It's always something people have been proposing, but it does have some challenges with it because the sensor itself is not only sensitive to axial strain state, much like a strain gauge, but it's more sensitive in the transverse direction than a strain gauge, which can be accounted for in normal, operations. But a fiber Bragg grating with its transverse sensitivity is more sensitive to the complete strain state. And so it does require several disciplines that need to be looking at this kind of at the same time. Having an understanding of sensor, and especially strain gauges and strain sensing measurement technology, understanding the measurements and mechanics involved in the strain states and strain transfer. The composite materials is also an issue. If you get these lenticular pockets that develop because you've embedded incorrectly, which are shown here, you have to have an understanding of the wave propagation, electromagnetic fields, all those things, and also having a background in strain system technology. So it is a challenge. You can't just blindly install these inside a composite and hope that you're going to get valid measurements right off the bat. So what we did was we have embedded these fibers in several composites at this point, but this one is one that was addressed. This program that I'm showing now was addressed to try to understand these measurements and the accuracies involved by installing these or embedding the fiber Bragg grating arrays inside composite overwrap pressure vessels, which these vessels are currently even flying on the station. They're being also proposed for hydrogen fuel cell powered cars. So these are ubiquitous. They're going to be everywhere. And the problem with these is they have a metal liner, which you can't see, and they have a composite overwrap, which you can see. But the interaction between those is making the prediction, or the prediction of failure, that much more challenging. They burst in something called stress rupture, which is not completely well understood given the complexity of the structure that we're talking about. So our goal here was to see if we could sort of unpeel the onion a little bit in understanding what these measurements meant. And the way we did that, well, first of all, the goals involved were we wanted to do real-time monitoring. We installed about 1,600 sensors on these bottles, 800 of which were embedded inside. The other were on the surface. And the goal was if we can develop a robust early warning indicator of the onset of catastrophic failure. So that's what our goal has been. And the nice thing, as I mentioned, is that we can provide these finite element-like experimental strains in real time to allow us to do health monitoring and also to validate the designs for future improvements. But the approach that we took, how are we going to discern the strain measurement and understand what it really means in terms of its physical significance? So what we did was we took these bottles through a collaboration with White Sands Test Facility, being sponsored by the NASA's NDE working group, and we installed the fibers. We had to develop some attachment techniques because they're somewhat challenging surface roughness. So we developed our surface attachment techniques, installing the fibers on the composite, then testing that to an 80% level of burst, and then overwrapping those fibers with another layer or 4 layers of composite windings on top. So those surface-mounted sensors are now embedded, and then we install another set of sensors identical to that layout on the outer surface. So we have both surface-mounted and we have embedded sensors, and tested those up to failure, see if we can see what's going on with those measurements. So that was the test and the goals. And what I'm showing here is some of the installation methods. If you have any questions about how to install fiber on rough surfaces, this is something that we had to work with a little bit. We had some failures initially, but we developed some transfer patterns. We had to develop some new techniques on how to mask and fill in the voids to these base coats. Sanding and surface prep was something we worked through, and successfully were able to test these out at White Sands at NASA's White Sands facility. So that shows you that. And just some preliminary, actually these aren't preliminary results. These are results that came as a result of the first level of testing. It looks like something got a little messed up here on our actual data, but yeah, so what I'm showing is a schematic on the lower left is the red line there. In this bottle we had sensors that were embedded in the hoop direction, or the circumferential direction, from 0 to 360. And what was hopefully being shown here is that, yeah, the horizontal lines are an aberration. What hopefully you can make out are the pressure cycles as we successively increase the pressure from one load to another load condition. And we are showing very good results in correlation between the embedded and the surface-mounted sensors, which isn't the same thing if you were to go axially or any off-axis directions. We end up getting some measurements that we've now begun to understand and how to correct for that. But with that, we'll go to the next section, which is dealing now not only in embedded and strain in composites, but looking at some work that we've done in magnetic field measurements. So as in this case, we're collaborating with UCLA, and the goal has been to develop a magnetic field measurement with fiber Bragg-rating technology. So by altering the sensor and incorporating that sensor within the architecture that we've already described earlier, that Alan described, is to have one system that can have strain, have applied loads, 2 and 3D shape, liquid level, and one that would measure on another channel magnetic field all at the same time. And in this case, what I'm showing is some very top-level cursory results, but very promising at this point, that we've been able to alter the sensor and show that with that altered configuration, we can have a sensor that's sensitive to applied magnetic field. Now, the big challenge here is sensitivity for people making these types of measurements, and so that is our the holy grail if we can get the sensitivity increased. So we're looking for opportunities to continue to partner with others to help us with that, but we have been able to correlate well between our experimental and our theoretical results. And then as I move around this one step further, on this fiber optic flower, we're moving from magnetic field now to the last area, which is in thermal protection health monitoring. And we're partnering in this case with CSIRO in Australia to monitor MMOD, impact damage. MMOD is the micrometeoroid orbital debris. You might think of it as space junk. We all are pretty familiar with that. That's a big challenge for NASA. How do we, in this case, detect and evaluate that MMOD? And our approach is to marry these two technologies, these somewhat disparate sensing technologies and modalities together into one concept with acoustic emission and thermal and the fiber optic temperature measurements, as you can kind of see here. So the principles that we're talking about are detecting and locating impacts using acoustic emission networks, and also evaluating the damage by using embedded fiber Bragg-rating thermal sensors in a very novel arrangement, which is a network that allows us to have some robustness. If we do lose one of the fibers, we can rearrange that either in a centralized or self-organizing way to be able to account for those differences in the or damage that might occur due to impact. So that's work that's ongoing, and what we've currently done so far is come up with an architecture and built a test setup that allows us to evaluate this network and this TPS health monitoring system. CSRO is showing on the left side here the two segments together on this novel arrangement that has ceramics serving as the insulation, and what we're doing now is building up for a large-scale test at NASA Dryden on a heat shield test structure. So with that, I guess the last chart before we get into the commercialization part is, where is all this headed? Right now, we've been working probably for the last year and a half with Kennedy Launch Services Program to see if we can incorporate as many of these technologies onto a future flight demo on a launch vehicle. So our first steps that we've been working toward is getting our system ruggedized that allows us to perform in this very hostile environment. But the goal is that we eventually want to, first out of the gates, we want to be able to do strain and temperature, and then see if we can get inside these cryogenic tanks with liquid level. And you can see all these aspects being really fused together, culminating with a flight demonstration, say in a year and a half to 2 years on a vehicle, on an expendable launch vehicle. So that's kind of the exciting part of this. We're looking forward to where this might take us, and again, with a single system, we're hoping to be able to acquire these measurements at these hundreds of hertz levels and be able to provide this with the robustness that the environment does require. So with that, I'll turn it over to Alan for the licensing.
As we have walked around the flower, we have demonstrated NASA-developed technologies and their validating applications. Technologies that can be licensed from NASA to fit into your application that will hopefully provide information that you never thought possible. To give you an example, 4DSP, who is one of our partners we've been working with for some time now, has licensed some of these innovations and now have made commercially available systems that can accomplish these types of measurements. And with that, I want to turn it over to Ron to do some further commercialization.
Okay, thank you, Alan. We have limited time, so I want to just quickly say that we're very happy again to have the opportunity to highlight this technology. To learn more about NASA Dryden and licensing opportunities, we provide here some websites to be able to link to contacting us, as well as the commercial partner we have for DSP. So with that, I'd like to turn this over to the question and answer, Bruce.
Yes, gentlemen, that was an excellent presentation, and you can tell by the quality of the questions we got in. So let's get started. Can you have both temperature and strain measuring on the same fiber?
The answer to that question is yes. When, say, for instance, you have a 40-foot long fiber, you bond 20 feet down to the surface, that measures strain. And if you wanted to leave the other 20 feet, you can put that inside of a small, little, tiny polyimide tubing, and you bond the tubing down to the surface, and in that 20 feet you're measuring temperature. So in that sense, you can measure temperature and strain using the same setup.
In field applications, what is the expected life of an embedded sensor?
Yeah, that depends on obviously the load environment. For surface-mounted applications, I know that we've installed these fibers on an F-18 back in 1999, and those fibers are still working. So surface mount, once you get the fiber installed, really the longevity of the fiber and its performance is very, very high. So I think we've been successful there. embedment depends on what we're talking about. If we're talking about embedding an optical fiber inside a COPV, what we found is, it depends on the pressure, and we have had some failures with these fibers about 5,000 psi, and I think partly because that's probably the most extreme embedment application that I can envision, because it's not only just like on a flat plate inside a plain stress kind of a test article. It's inside a pressure vessel that has axial loads. But primarily it has these pressure loads that are crushing the embedded fiber. So these optical fibers, the structural fibers that are going sort of longitudinally around the fiber, is beginning to crush that and create these high stress intensity factors on the fiber. So having said that, the sensors themselves have actually performed pretty well up to about half or maybe 3/4, well, probably more like half, just to be safe, of the burst pressure. But they do fail if, at some point, if you cross the fibers and you begin to get some stress concentrations on them. In terms of on a flat plate, we have not had any issues. I'm talking now not filament wound. I'm talking more of a quasi-isotropic laminated composite, and the strain to failure has been quite high. In fact, we've tested those up to almost failure, and they performed well. So hopefully that's answering the question there.
Is there a minimum radius of bending?
We've kept our the fiber bend radius to about 1/2 inch.
Okay. What is the bandwidth of the ADC used to sample the return signal, and what is the laser pulse rep rate?
Our A to Ds run in the tens of megahertz, so it's not uncommon for us to run at about 40 megahertz, and the repeat rate of the laser is basically your sample rate. So it can repeat 20 times a second. That gives us a 20 samples per second sample rate, or 100 times per second, which gives us 100 samples per second. And the tuning rate of the laser, basically sets that repeat rate. How fast can we mechanically tune that laser governs our repeat rate.
With FOSS, how does strain resolution vary with gauge length, separation, and measurement frequency?
Yeah, in that case, for most applications, the strain over that gauge length is pretty uniform. It depends, again, on the application. If you have high strain gradients, that might be a problem, but I think what we end up getting out of our highly discretized fiber is the gauge length of about 1/16 of an inch. So that helps to kind of average out any strain gradients. We have seen in that composite overwrap pressure vessel example that where if you get a tow or composite filament impinging transversely on the fiber, we can get sort of a grading within a grading, which is called chirping in the fiber optics world. And what we've done to accommodate that or account for those kind of errors is discretize that even further until we get a very uniform gradient along the gauge length. So we have the flexibility that you don't have with the strain gauge, which is we have the ability to on the fly change the gauge length to make sure that we have a uniform strain gradient. Hopefully that's in the separate. How does the strain resolution and then separation and measurement frequency? So I think I hopefully answered that.
Yeah.
Okay.
Is it possible to estimate the shape of non-uniform deflections in the wings?
Possible to estimate the shape of the non-uniform deflections in the wings?
Yes.
Yeah, I think if I'm understanding that correctly, non-uniform deflection, what it really gives you is the ability to resolve deflections into a very fine way. I guess I'm not quite sure if you say non-uniform deflections, are these deflections that have high deflection gradients? Or are you talking spatially, or are we talking in another way? So
let's assume that they're talking spatially.
Yeah, I think the nice thing about this, if you get a very flexible structure and you have higher deflection modes, we're able to see those higher deflection modes just because it's based on the radius of curvatures, and you can refine that because of our measurement fidelity, we can get a lot of points along that curve. So yes, that's something that we can do fairly accurately. If there are any questions here for the people that pose these, feel free to contact us. We'd be happy to interact with you on any of these questions. So you have our contact information, and please feel free to. We'd love to be able to talk to you about your specific application. In many cases, in this case, it's really hard in this forum, but we'd be happy to do that offline.
Well, I'm glad you added that, because I'm afraid that's all the time we have. I'd like to thank our team of experts for giving us such an informative presentation, and I'd like to thank today's attendees for participating. That concludes today's webinar, sponsored by Luna Innovations, Oz Optics, and TechBriefs Media. However, the complete webinar will be available on demand for the next 12 months at www.techbriefs.com. And for those questions that we did not have time to get to, someone from NASA will be responding at a later date via email directly. Thank you all for participating. Good afternoon.